This video present our new paper entitled RCooper, a real-world large-scale dataset for roadside cooperative perception, which has been accepted by CVPR 2024. Let's start with a general overview about why roadside cooperative perception is important. Roadside perception is significant for higher-level autonomous driving and intelligent transportation, attracting wide attention from both academia and industry. However, current research on roadside perception mainly, urgently necessitating roadside cooperative perception to enhance road scene understanding, focuses on independent viewpoint perception, constrained by a single sensor view, which results in limited perception range and blind spots. Roadside cooperative perception is a challenging task, but the lack of datasets hampers exploration in this field, as shown in the left figure. We released the first real-world large-scale roadside cooperative perception dataset, RCooper, filling the current industry gap of such datasets. And as shown in the right figure, aims to support regional-level, all-time traffic scene understanding in high-level autonomous driving research. Then, come to the second problem: what are the advantages of roadside cooperative perception? As shown in the figure below. Firstly, it significantly expands the perception range of LiDAR, achieving comprehensive coverage of road sections, and multi-angle cooperative radar perception can mitigate the impact of viewpoint obstructions in complex intersection scenarios. Secondly, it effectively reduces the perception blind spots of cameras. The area under the poles is the blind spot for cameras, where adjacent cameras can complement each other's views and perceive the blind spots. Let's turn to the dataset section. The roadside cooperative perception dataset RCooper was collected from Nanjing, China, encompassing two typical roadside scenarios, intersections and corridor. The dataset was built with scenes from different times and weather conditions throughout the year to enrich the diversity of natural environments and lighting conditions. And considering the characteristics of scenes and the cost of construction, 3 sensor layout schemes were designed for 2 scenarios, which is shown in the right figure. We sampled the most representative 410 scenarios, each lasting 15 seconds, at a rate of 3 Hz. The final constructed dataset comprises 30K frames of LiDAR point clouds and 50K frames of images. The dataset annotations are tailored for typical perception tasks, including detection and tracking. To obtain high-quality annotation that supports perception tasks, a 3-step annotation method was employed, consisting of single-view manual annotation, automatic cooperative annotation, and manual refinement checks. The datasets is visualized in the right 4 videos. Let's move on to the task and benchmark section. The roadside cooperative perception dataset RCooper is available for downstream perception tasks. We select roadside cooperative detection and tracking as demonstration applications and present benchmark experimental results to pave the way for future research and scenario applications. As for cooperative detection benchmark methods, we select early fusion, late fusion, and SOTA-middle fusion methods, including ATT-Fuse, RCooper, Where2Com and CoBVT. As for cooperative tracking benchmark method, we select classic AB3DMOT. The perception metric is shown in the right tables. It can be seen that the cooperative methods outperform the single-view method. However, interestingly, some SOTA methods are inferior to naive ones. The perception visualization in both scenarios are shown in the right videos. It can be seen that objects are accurately perceived. At this point, we summarize the result analysis and findings. Firstly, we can see collaboration is better. When coming back to the metric page, we can see cooperative methods outperform single-view method. Secondly, we can see some SOTA methods fail in roadside cooperative perception. When coming back to the metric page, some SOTA methods are inferior to naive ones. 2 possible reasons are analyzed below. Scenario gap may be the transparent reason. Vehicle-centric SOTA methods struggle in roadside feature encoding since specific challenges, for example, larger variations of heights and pitch angles. Besides, as shown in the right figure, data heterogeneity introduced by the integration of multiline and MEMS LiDARs weaken the perception performance in intersection scenes. Before the end of video, let's briefly recap what we have discussed here. Firstly, to extend the boundaries of both autonomous driving and traffic management, roadside cooperative perception, RCooper, the first real-world, large-scale dataset, is released in this paper, which is expected to boost roadside cooperative perception towards round-the-clock area coverage perception for a restricted traffic area. Secondly, our dataset consists of high-quality manually annotated sensor data groups, 50K images and 30K point clouds, covering two typical traffic scenes, i.e., intersection and corridor. Thirdly, a competitive benchmark is constructed to pave the way for subsequent research, and the experimental results demonstrate the effectiveness of roadside cooperation perception and reveal the direction of future work. Thank you for your attention.